Okay, let's start. So we are studying ordinal numbers. Yeah, ordinal numbers denote positions in lists, but we also want to list infinitely many objects at the same time, so we need the concept of infinite ordinals also. So ordinals we defined as transitive sets that are well ordered with respect to the membership relation. So we already know some examples of ordinals. 0 is an ordinal, 1 is an ordinal, 2 is an ordinal. In general, every natural number is an ordinal. And then we would like to say that, omega exists because of axiom of infinity, but we would like to say that omega is also an ordinal. Okay, so once you prove that 0 is an ordinal, which is statement number 1, then statement number 2 gives you that 1 is an ordinal, 2 is an ordinal, 3 is an ordinal, and so on. Correct? If alpha is an ordinal, then alpha plus is also an ordinal. However, so far we haven't really understood why omega is an ordinal. We can prove it directly. We can prove that omega is a well-ordered set with respect to membership relation, and also that omega is a transitive set. Those two are easy to see. However, we would like to make this idea of taking limit ordinals precise. Okay, the limit ordinals are obtained via this third condition. It says that if you have a set of ordinals, then their union is also an ordinal. Okay, so let us try to prove this statement now. So for second statement we have proven. First, there is nothing to prove. Yeah, so these are, let me say, 0 is a specific example. Then these are called as successor ordinals. And third one, the things which you cannot obtain by number 2, the remaining ones are called limit ordinals. So it's not necessarily just the third one. Yeah, only a subset of them. Anyway, so maybe I should write, limit ordinals not obtained, not successors. Yeah. But for that we need 3. Okay, so let's try to prove the third statement. So if beta is equal to union of S, so let me quickly remind you what is union of S. It is the union of all the elements of S. Okay, so if I say that alpha belongs to beta, then what do I really mean? Then alpha belongs to some gamma, where gamma belongs to S. Okay, so if you understand that, then what should we prove? We need to prove 2 things. First thing is that beta is it is a transitive set and that it is well ordered. Okay, so how will we show that beta is transitive? In order to show transitivity, what do we need? So suppose gamma is an element of beta, then what will happen? We just said that then gamma belongs to alpha for some alpha in S. See, beta is union of S. So which means every element of beta is actually an element of some element of S. Right? That's what the union means. Then what will happen? Now gamma belongs to alpha. So what will happen? Because alpha is an ordinal, S is a set of ordinals. Since alpha is an ordinal, alpha is transitive, and hence what can I conclude? If gamma is an element of alpha, then I can conclude that gamma is a subset of alpha. Very good. Okay, so we know that gamma is a subset of alpha. So therefore, what do we know? That every element of gamma is an element of alpha. And every element of alpha is an element of beta. Since beta is equal to union of S and alpha belongs to S, alpha is a subset of beta, and therefore gamma is a subset of beta. So this part is proved. Yeah, gamma is a subset of alpha, alpha is a subset of beta, so we are done with this part. Then next thing to show is that beta comma membership relation is a well order. Now this is slightly tricky. Yeah, is a well order means it is a well ordered set, wo set. Okay, this is slightly tricky. So what do we need to show its well order? We start with, what is the definition of a well order?
Every subset has a least element.
Every, no, please correct that. Not every subset has a least element. Every non-empty subset has a least element. Okay, so let empty set not equal to T subset of beta. So which means T is a non-empty subset. Now we want to find the least element. Now imagine, imagine that our S happens to be 2 and 4. Yeah, just two elements, 2 and 4. Then what will, if I start with some T, then what will be the minimum element? If I start with 2 and 4, what will be the union? What will be S first of all?
It will be 4.
Please think about it. Yes, it will be 3. Yeah? Union of 2 and 4 is 3. Wait, no. See, 4 contains 4 elements. So what will happen? It contains 0, 1, 2, 3. 4. Right. Okay. So this is 4. But if I start with a non-empty subset of that, then whatever element I have chosen in T, yeah, because, so therefore, then alpha belongs to T, correct? For, maybe I should use a particular notation. So let gamma belongs to T, and then what will happen? Then gamma belongs to alpha for some alpha in S, not in beta. Everything is about the membership relation, right? So if so gamma is T is non-empty, so it must contain some element. So I chose that element. Now that element must come from some element of S. Okay, so then gamma belongs to alpha for some alpha in S. So now what happens? So therefore alpha intersection T is non-empty. Why is it non-empty? What does it contain? Gamma. Very good. So gamma is an element of alpha intersection T. Now I am going to claim, so let rho be equal to minimum of alpha intersection T. Rho be the least element of alpha intersection T. See, why can I do that? Yeah, rho exists since alpha intersection T is a non-empty subset of alpha in On. Correct? Alpha is an ordinal and alpha intersection T is a subset of alpha and it is non-empty. So therefore, what like by the well-ordering property of alpha itself, alpha intersection T must contain a least element. I am just going to claim, yeah, I will add a new page now. So claim that rho is also equal to the minimum element of T. So see, the process is quite simple. What you are doing is that you are collecting different ordinals. You are taking union of different ordinals. But all of those ordinals have the same initial string. Everything starts with 0, 1, 2, 3 and so on. So therefore, whenever I hit non-empty, yeah, I mean that gamma in particular, so then the minimum element has to be an element of that gamma. Yeah, it will be below gamma and the points until gamma are present in everything in there. So therefore, whether I choose a different alpha, like alpha minimum of alpha intersection T is same as minimum of alpha prime intersection T whenever we choose some different alpha prime such that alpha prime intersection T is non-empty. Whenever you have something non-empty, then the minimum will remain the same. Okay, now that we are talking about this, yeah, rho is equal to minimum of T. How do we prove that? So here we need to use trichotomy of ordinals. Yeah. So I will write it in a different color. So trichotomy of ordinals given alpha and beta in On, either alpha is equal to beta, alpha belongs to beta, or beta belongs to alpha. Right, so this is same as our usual trichotomy. The only thing that I have changed is that I have replaced less than by membership relation. Okay, so this is what we need to use. So let gamma prime belong to T. Okay, so let me go back slightly and see. So T is a non-empty subset of beta. We want to argue that minimum of T is the minimum of alpha intersection T. So rho. Now if I take an arbitrary element of T, then what should I show if I want to show that rho is minimum? Rho is either equal to or less than. So less than or equal to an arbitrary gamma prime. That's my claim. Okay. Yeah, we need to show gamma prime is less equal rho, i.e. Gamma prime is greater than or equal to, yes, correct. I.e. gamma is equal to rho, gamma prime is equal to rho, or gamma prime contains rho as an element, right? So that's the only thing we can show. Okay, so assume maybe not assume, maybe let's say suppose. So suppose gamma prime is less than rho, then we should arrive at a contradiction, right? So what will happen? So gamma prime is less than rho, i.e., less than is same as belongs to. Gamma prime belongs to rho. By the way, these things need a proof, I am just not doing them. Yeah, less than and belongs to are identical for ordinals, that needs a proof. For natural numbers it's easy to see, but for all ordinals it needs a proof. Okay.
Isn't that the definition for ordinal less than?
But like maybe I am referring to trichotomy. Trichotomy needs a proof that given any two well-ordered sets, either they are isomorphic or one is isomorphic to an initial segment of the other. Yeah, that needs a proof. Okay, so suppose gamma prime is less than rho, i.e. gamma prime belongs to rho, then what can we say? Since rho belongs to alpha and alpha is transitive, rho is a subset of alpha. Yes? Are you clear about this? Yeah, rho is an arbitrary, rho is some particular element of alpha, therefore rho is also a subset of alpha. So in particular, so therefore gamma prime, what can we say about gamma prime? Gamma prime is an element of rho. So gamma prime is also an element of alpha. Okay. So where was gamma prime? We started with gamma prime in T. So therefore now gamma prime was in T, we concluded that it is in alpha. So therefore gamma prime is in alpha intersection T. Now do you see the contradiction? Yeah, which is a contradiction? Rho equal to minimum of alpha intersection T. Yeah, if gamma prime is strictly smaller than rho and it is in alpha intersection T, then our choice of minimum was wrong, and this thing completes the proof. Yeah, that rho is actually the minimum of T. Any questions? Yes.
How does rho being the minimum of T makes beta rooted? We have to prove that minimum of
Yes, okay. So beta, we started with a non-empty subset of beta, and now we concluded that rho, whatever we found, is actually minimum of T. So we found the minimum, like the least element of T. So therefore beta is a well-ordered set because T was arbitrary. Any other questions? Fine. So now we have shown the third property also, that union of a set. Yeah, please remember, union of a set of ordinals is again a set. Is again an ordinal. Okay. So as a corollary, yeah, we are going to prove that On is a proper class. So we said that On is the class of ordinals, class of all ordinals. But so far we haven't determined whether it is a set. Yeah, I mean all classes are either proper classes or sets. Okay. So we are going to prove this, that On is a proper class. So suppose for contradiction that On is a set. Then what can we do if you have a set of ordinals?
Take the union.
Take the union. Yes, so let beta be the union of On. Yes. Then by 3 above, what can I conclude? Where does beta live?
In O.
Beta is again an ordinal. Correct? We just showed that a union of a set of ordinals is again an ordinal. So we have assumed that On is a set, so beta is the union of a set, so therefore it must be an ordinal itself. Therefore, what can we say? Well, moreover, by 2 above, what can we conclude? That beta plus is also in On. Beta plus is also an ordinal. Okay, so now what happens?
On is an element of On.
Beta is an element of beta. Yes. So, but beta belongs to beta plus. Correct? And what is the union? Like union of beta plus will also contain, just a moment. Yes. And hence, see all elements, so beta plus is an ordinal, so therefore all elements of beta plus are elements of union of On. But union of On is beta, so in particular beta belongs to beta, and what is this contradiction to?
Axiom of foundation.
Yes, this is which is a contradiction. So therefore, yes, this process of taking ordinals, it doesn't stop. Okay, so now that we have established this, let us revisit our list. Okay, so 0 is an ordinal, we established that. Then 1 is an ordinal because of 2. Because of 2 means not the number 2. Yeah, the property 2. 1 is 0 plus, 2 is 1 plus, 3 is 2 plus, and then omega is now a union of set of all the natural numbers. Okay, so therefore omega is an ordinal. Omega plus 1 is again the plus, right? So these jumps, yeah, I'm going to highlight these. These jumps are limit ordinals. I have mostly only written limit ordinals in this list afterwards. But the point of this last corollary is that we will never stop. Yeah, this dot 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 will actually continue. Okay, so what is omega 1? So in particular I should highlight this. Every limit ordinal is every limit ordinal beta satisfies beta equal to union of beta. Yeah, omega is equal to union of omega. Omega plus omega is equal to union of omega plus omega. Yeah, we will never stop. So omega 1, which is the first uncountable ordinal, yeah, that is also union of all of them. Yeah, so this is the first uncountable ordinal. Okay. So that means last time we partitioned these things into something. You remember this? Yeah, so then starting with omega until omega 2. Then starting with omega 2 until omega 3. Yeah, but not including omega 3 and so on. So all these partitions are important. What do they indicate? These green brackets, what do they indicate?
They're all in bijection.
They are all in bijection. So last time I said something and perhaps some of you were confused. So I will do it again. So what is omega plus 1? Omega plus 1, what are the elements, please tell me? Omega plus 1, we can list all the elements of a well order. So is 0, then less than 1, less than 2, less than 3 and dot dot dot, and finally we have omega. Now I am going to say that this is countable. Why? Because it is union of two countable sets. Omega is a countable set and singleton is a countable set, so union is countable. Now one way of saying it's countable is to establish a bijection. So why not do this? I take 1 here, 2 here, 3 here, 4 here and dot dot dot, and at top I put 0. I mean, this is not the usual ordering. Yeah, please don't worry about like 1 being less than 0. This is not the usual ordering, but this establishes a one-to-one correspondence, right? This gives me a bijection between omega plus 1 and omega. Can you tell me how to write omega plus 2 now?
2, 3, 4 and 0 and
2, 3, 4 and then 0 and 1 at the top. Yeah, 0 less than 1. What about omega plus omega? Odd and even. Yes, so that's what I wrote last time. Yeah, so 0 less than 1 less than 2 and dot dot dot, then omega less than omega plus 1 less than omega plus 2 and dot dot dot. Yeah, so then I can say, well, I can choose something different this time. 0 less than 2 less than 4 and dot dot dot, and then 1 less than 3 less than 5, and you can choose a different bijection. So these are all bijections. Yeah, they don't preserve order. So we actually borrow the order from the ordinal. Okay. Well, I don't want to go further. Yeah, like omega to the omega is also in bijection with omega. Epsilon naught, which looks so big, that is also in bijection with omega. Okay, if you are interested, you can explore these things, but it takes time. Okay, so that's why I'm not going to do it here. However, now this is raising some natural questions. When I write omega plus omega, what do I really mean? You understand? We haven't specified the arithmetic of ordinal numbers so far. And the way to do that is to use transfinite recursion. Okay, so what is recursion? It is a way to define something for all natural numbers. And what is induction? It is a tool to prove something for all natural numbers. Now here I am saying transfinite. Yeah, you have heard the word. Yeah, trans is beyond. So beyond finite. So beyond finite means indexed by ordinals actually. So let us do that. Transfinite recursion and induction. Okay, so how do we prove this? Well, the answer is simple. Well, suppose P is a property of ordinals. Okay, then assume P of 0 is true and for all beta in On, whenever P of alpha is true for all alpha less than beta, then P of beta is true. Then P of alpha is true for all alpha in On. If I replace On with natural numbers, then which form of recursion is this? Strong. Yeah, so for ordinals we can only use strong recursion and strong induction. I'm sure you can see why. Yeah, what is the problem? Limit ordinals. For limit ordinals are not successors of anything. So it doesn't make sense to use weak induction. Right? If you want to prove some result for omega, then you cannot really do that. Okay, so recursion and induction, the names will remain the same. If you want to define something, then you use recursion. If you want to prove something, then you use induction. Okay. Okay, so let me define these things now. So now I am going to describe ordinal arithmetic. And by arithmetic I will define addition, multiplication and exponentiation, and that's all. And how do I define it? Well, again using transfinite recursion, the same formulas actually. So how do we define addition? The same way that we defined it for natural numbers. So alpha, so let alpha be an ordinal. So addition we will define by this. So alpha plus 0 is defined to be, any idea? Alpha plus 0 has to be alpha. Okay. Then I should do it for successor and limit ordinals. Well, so alpha plus beta plus will be defined to be, very good, so all of you know what to do. And if gamma is a limit ordinal, then what will we do? Alpha plus gamma is defined to be, it will be defined to be union of alpha plus delta, where delta is less than gamma. That's all, when gamma is a limit ordinal. Okay, so let us look at one example. Well, what will happen with 1 plus omega? What is 1 plus omega? Which definition should I use? Third one. So 1 plus omega is union of 1 plus n, where n is less than omega. Right? Whenever we know it's a natural number, we can use n. So what is it union of? Well, 1 plus n, what is the union of all such numbers? Yeah, because I am starting with 1, 2, 3 and dot dot dot, correct? So this is omega itself. Okay, so 1 plus omega is just omega. On the other hand, omega plus 1, well, what is it? Omega plus 1. Which definition should I use? Second one. So this is omega plus 0 plus. Okay, I am making a mistake. I shouldn't really say defines. Yeah, the colon should not be there. Yeah, this is just our ordinary thing. So what is omega plus 0? Which is omega plus 1. Yeah, I mean, I'm just playing with you. Yeah, but I wanted you to understand what's really happening. So omega plus 1 is the notation for omega plus. Yeah, I mean, that's what we showed. Still there is something, but the important thing to observe is that these two are not equal. So the first thing, as soon as you enter the arithmetic of infinite numbers, ordinal numbers, addition is not commutative. Right? This is the first and striking property of ordinal arithmetic. It is associative, but it is not commutative. In fact, you can also describe, if you are given some beta less than alpha, then you can find a unique gamma such that beta plus gamma is equal to alpha. Maybe I should write this down. Yeah, we are not going to prove it, but maybe I should just note. Given, maybe I should first note this property, that addition is not commutative, but it is associative. Okay, this is note 1. Let's say note 2, that given alpha less equal beta, there is a unique gamma such that alpha plus gamma is equal to beta. However, yeah, I mean, be warned, whatever I am saying, that's only true for the order in which I am saying these things. So I am not saying that if alpha is less equal beta, then there exists a unique gamma such that gamma plus alpha is equal to beta. Okay, if I change alpha plus gamma to gamma plus alpha, it's no longer true. Right? Only in one direction I can have this. Yeah, sometimes this is used to define subtraction. Yeah, beta minus alpha is that gamma. Okay, so this is addition. Let's make things more exciting and define multiplication. Well, now you know the pattern, it's not going to be very exciting. So alpha dot 0, what will it be? 0, yes. Then alpha dot beta plus it will be alpha dot beta and plus alpha. Very good. And alpha dot gamma, well, no surprise, it is union of alpha dot delta, where delta is less than gamma, where gamma is a limit ordinal. Once again, I invite you to compute 2 dot omega. 2 dot omega is union of 2 dot n, where n is less than omega, 2 dot n is union of 0, 2, 4 and dot dot dot. Even though certain elements are missing here, they are included in the next one. Yeah, even though 3 cannot be seen here, 3 is an element of 4, so it's already present in the union and this will turn out to be omega. However, omega dot 2, what is it? Omega dot 1 plus. So, it is omega dot 1 plus omega, which is, well, again for the first one, what is omega dot 1? Omega dot 0 plus and plus omega. Well, what is omega dot 0? So 0 plus omega and plus omega. Now there is an assignment question to show that 0 plus anything is that. Okay, so prove that using transfinite induction, and then this will turn out to be omega plus omega by associativity and showing that 0 plus omega is omega. Okay, so this is much bigger. Yeah, omega dot 2 is much bigger than 2 dot omega. Again, it is not commutative, but it is associative. Okay. Finally, exponentiation. What will be alpha to the power 0? 1. Alpha to the power beta plus. Very good. Dot alpha. So we always use the previously defined operation to define the new one. And what will be alpha to the power gamma? Union of alpha to the power delta such that delta is less than gamma. Yeah, if gamma is limit. Well, let's not look at any examples, but you sort of get the feel. Yeah, I have given you lots of questions in the assignment to compute certain ordinals, simplify them, so that you will get used to these things. Okay, one more property of ordinals is that even though, I mean, look at this chain, yeah, this chain, it's an increasing infinite chain. Even if I want to just talk about omega plus 1, it contains 0, 1, 2 and then dot 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 and then omega. So there are infinite ascending chains, infinite increasing chains. However, the way we have defined ordinals as transitive and well-ordered sets, the well-ordered property ensures that there is no infinite decreasing chain. Wherever we go, okay, so tell me some place I should start. Yeah, I will use yellow color and I will start somewhere in this picture, and I will try to show you that no matter whatever decreasing chain you choose, it will be still finite. Tell me where I should start.
Omega 1.
Omega 1, okay, so I started here, omega 1. Now I want to find something smaller than that. As soon as I say that, I have to leave out infinitely many elements in between. Yeah, omega 1 is a limit ordinal, correct? So therefore I have to make jumps. Okay, what will be the next element? Any suggestions? Yes? Right?
When you define it for exponentiation, can alpha be a limit ordinal?
Huh?
Can alpha be a limit ordinal?
Oh yes, alpha can be anything. So we are not defining any of these operations as binary operations. Yeah, we are only defining them as unary operations. Alpha is fixed and then you are defining this. So actually I have given you some exercises to work with these things. Yeah, well, like while changing alpha, what happens? So you have to see that.
I understood when it is a successor ordinal, but if it is a limit ordinal, we are calculating again limit ordinal to calculate that limit ordinal.
Yes, so I mean ultimately see, don't get confused by the union notation. Unions are not always limit ordinals. Yeah, union of 1, 2, 3, 4, that's not a limit ordinal. However, in this case it will turn out to be. Yeah, I mean those are all results, but we don't have enough time in this course to go through all these properties. Okay, so yes, omega 1, we have to find a decreasing chain, potentially infinite decreasing chain. Tell me what other ordinal I should choose smaller than omega 1. Yes?
Epsilon 1.
Epsilon 1, okay. After epsilon 1, well, you can tell me epsilon naught plus 1 million. Fine. From that I can make jumps, one step jumps. Epsilon naught plus 1 million minus 1, then 1 million minus 2. But again that will be something finite until I hit epsilon naught. Then after epsilon naught, because it's a limit ordinal, I have to make a jump. Maybe I will go back to omega square plus 1. From omega square plus 1 again I can take this one step down, down, down. But as soon as I hit a limit ordinal, then what will I get? I again have to make a jump. So between, so omega square, yeah? So out of omega square, like between omega and omega square, I will have to hit some omega dot n plus m. Correct? So then again, so that n plus 1, n plus 2, etc., infinitely many values of those n's are missing out. So therefore, maybe I will hit this number, then I will hit this number, then this number and this number, then again I will hit something here, but ultimately whatever I do, it will be finite. So this is called well-foundedness. Yes, we have seen well-foundedness, axiom of foundation, that every decreasing chain of belonging relationship, the membership relationship, is always finite, and that is also a property of all the ordinals. Right? So ordinals are well-founded. I have asked you to prove this in the assignment. Yeah, i.e. the decreasing chain condition holds. There is no infinite decreasing chain. Okay, this is a property. Then one more property I think you would be interested in is ordinals have a division algorithm. Yeah, it looks really weird arithmetic, but it has some nice properties. So I'm just going to show you something specific. So given alpha in On, there are unique beta and gamma in On such that alpha is equal to omega dot beta plus gamma. Oh, I should say gamma in omega, actually. Gamma is finite. So what I am saying is that this is the quotient and this is my remainder. So I can divide every ordinal by omega, I will get a quotient and I will get the remainder. The remainder has to be a finite number. Yeah, by finite I actually just mean that gamma is less than omega. Yeah, this gamma is less than this omega. I can divide any ordinal by any ordinal actually. I can replace this omega by something else and I just have to make sure that gamma is less than that replacement delta. So as a consequence we get several statements. If I divide by 2, then what will be the remainder? Either 0 or 1. So therefore ordinals are either even or odd. And every ordinal can be uniquely written as limit ordinal plus a finite ordinal. Yeah, this omega dot beta is limit and gamma is finite. Okay, so let us stop here for today.